bit more sustainably and imagine to have an on-farm small reservoir, a small pond, which basically collects the water during the off-season, the winter, or during the extreme intense storms when runoff is big, and then you have the water there for using when rainfall doesn't come. This is more sustainable in the sense that you're not tapping into groundwater, which is potentially a problem if the groundwater recharge does not proceed as fast as you're using the water, which is the case in many big aquifers. I'm sure you have been talking about this in all sorts of ways across the world. Now, there is an interesting trade-off, because of course, if you want to be sure not to run out of water for irrigation, then you want to have a big pond. But the depth of the pond is actually more or less fixed to 2 to 3 meters for construction, from building reasons. So implementing a big pond will mean that you are using a lot of area for the pond, and you're taking it away from your cultivable area. Now you start seeing here the trade-off again. I can be sure to have the water, but I'm reducing the cultivable area, which means that my maximum yield is decreased. Or I can go the other way around, gamble, go with a small pond, hope for the best. If water runs out, well, I will need to face the consequences. So now it's not just a question of what are the constraints and so forth. It's also my personal preference. Do I accept the risk of getting a low yield, or do I prefer to have a safe yield, but probably lower yield? So we try to answer this question, and the colors are off. That's okay, but that's interesting. Here you see the fraction of the farm area under cultivation. So this means here you have a small fraction of farm area under cultivation, big pond. On this other end here, you have all your area under cultivation, basically no pond, and everything in between. And on the y-axis, you have the average of farm, at the entire farm level, crop yield. We looked at 3 different climates, because of course climate change is of interest here. In blue, what we could consider current climate. In yellow, so the line in between, a slight increase in temperature, a slight increase in the length of the dry periods, and decrease in increase in the rainfall amount per event, but still same total precipitation. And then in black, the more extreme climate, warmer than the yellow, more extreme dry periods in terms of length, and bigger events. But still, total amount of precipitation is the same. Now, if your goal is maximizing the average yield, well, under these different climates, you see what you're supposed to be doing. You basically should be having a pond this size, and you should be, and not unexpectedly with this climate change, you probably need to go for bigger and bigger ponds. Good. Now, if your point though is to reduce the risk of achieving extremely low yields, then you're not so much interested in the average farm crop yield, but you're interested in being sure that you never or very unfrequently end up in very low yields. So we tried to see, okay, what pond would you need to have in that case. And here you have the ranges of this pond size for the same climatic conditions. And the interesting thing is that, in particular with climate change, you see that the vertical line, the conditions that maximizing yields, it does no longer fall into the range of pond size that would minimize the risk of low yield. So there is a disconnect, an increased disconnect between what you should be doing if you want to maximize the average yield and what you should be doing if you want to minimize the risk of extremely low yield. Again, this means that you are faced with an yield security trade-off. So, to conclude, I've tried to answer a different case to basically 4 key questions. First, how do crops respond to rainfall variability? I've shown at the beginning that there is a non-trivial relation between average yield and its variability, that parabolic dependence with the maximum standard deviation in Mexico condition. I've shown that there are all sorts of trade-offs when it comes to management of water and crop choice. There is an implicit trade-off in, well, first and foremost in yield and yield stability and water requirements and its variability. But there are also trade-offs when it comes to what kind of crop you should be using. These, as I discussed, has implications also under the point of view of sustainability. Perennial crops could provide a number of ecosystem services, but this comes at the cost of reduced yield, enhanced water requirements. And then finally, very quickly, the farmer's perspective, where the maximization of yield may not go in the same direction of avoiding the risk of extremely low yield. So there is again another trade-off, or if you want, different preferences may lead to different decisions.
Thank you.
Questions?
Yeah, thank you, grazie. And first, I open with a very simple question. And can we distribute your presentation to the students? And second question, can I make it available on the web?
Definitely distribute. Let me think about the web.
Okay, okay, so we can give it to the students and then we can get in touch on the web. Okay, that's great. Now, questions from the students first. Ready to ask a question? Yeah, please.
I have a question about how to study the relation between soil moisture, biomass, and the impact of rainfall and irrigation. So my question is, can we study this topic also with, I think about surveying techniques, remote sensing. So I'm thinking in particular about vegetable indexes. So if we can understand the needing of water of plants and consequently irrigate in a certain way. So I'm going to my question.
Yeah, I think I see at least a couple of, I mean, it's a wide question. I see at least a couple of pieces. So the first aspect is definitely, I mean, you can, but maybe the first aspect is, if I narrow it down a bit, can we use, for example, remote sensing to guide irrigation, the timing of irrigation? Yes, that's one of the approaches, mostly because they are mostly based on the NDVI, so the normalized differential vegetation index. Plants change color when they are under stress, so you see pretty quickly when they should be irrigated with remote sensing techniques. So yes, that's done. Most often the irrigation, despite this being possible, irrigation is done based on more simpler or less sophisticated system. There are very simple soil moisture sensors based on a gypsum block that could work, that are inexpensive and so forth. So there might be some level of checking of the soil moisture. Of course, this requires knowing how the crop responds to that soil moisture. So when you need to irrigate. Other approaches are, and some of these were used back already in the 90s, 80s and 90s, the simple soil moisture balance, so basically model. I'm thinking about back 80s, 90s, for example, in California, there was a system in which farmers would call a phone number to know whether they would need to irrigate or not. It seems like prehistory, of course. And that was based on a simple water balance with the knowledge of the amount of like potential evapotranspiration rate of an average crop. So simple but effective. The other aspect, yes, these results, for example, like the trade-off yield, the effect of irrigation on yield stability can be studied with for example, survey data. There are some countries, for example, the US, that keep a separate survey of yields at the county level. Separate between irrigated and non-irrigated, so that it's possible to see this effect.
Another question, yeah, please.
How do you estimate soil properties, practically speaking? For example, do you use drones in Sweden to evaluate the soil properties?
So the soil, I personally don't work in that area, but so the soil properties that are entering here are very basic soil properties. So it's basically soil porosity and hydraulic conductivity, which means that maybe it's not perfect, but if you have a sense of the soil texture, and that can be obtained in different ways, looking at the soil, or like seeding the soil, or one of those more hands-on, like simple, the clay method, so to speak. Then you can have a sense of those properties directly. So it's in this respect, it's relatively easy. You don't need so much information about the soil.
Other questions? Another one from the students. So let's leave the word to the general audience, but please, students, get together and ask one more question, okay? So questions from you?
Yes.
One? Okay, yeah. Go on.
In your model, how do you reproduce the phenological behavior of vegetation? What are the parameters that can reproduce the behavior?
So, I actually could be kicked out of SLU in 5 nanoseconds. I don't have the phenology there. The only aspect, the only aspect of phenology that is there is basically the length of the main growing season. What you've seen here is a fixed length, but in other projects we use the simple growing degree day model. So basically summing up all the daily temperatures when they are above a certain threshold, and then knowing that when a certain value is reached, then you reach a certain phenological aspect. They work pretty well. I mean, given the simplicity of those models, I would say I'm amazed how well they work.
So in that case, you're considering the temperature as one of the factors that can stress the...
Yes.
Students again, or last chance? Nobody? Okay, but next time I will be more strict. And other questions from you?
Yes.
No, there is a question.
Oh,
I'm not a student.
no, she's not.
Sorry.
Yeah, your question.
How do you measure the moisture in the soil? Or
There are 3 or 4 different techniques to measure soil moisture.
do you measure the moisture in different parts of the field?
Not behind this. I mean, we are measuring soil moisture in some places, but we didn't use the reason why we didn't focus so much on the measurements is that to study like the effects of variability, you need a long record.
Yeah, I know.
And so we have right now 8 years of data in one location in Brazil, but it's like not even sufficient, I would say. So that's why we work in a different way. But I mean, this model has been compared with some observations. It does reasonable things.
Last question, because then there
Yes.
is easy.
Does the rainfall variability reproduce all different climate conditions, like arid, continental, wet climate? Just because I'm curious about perennial and annual plants, if they behave differently in consideration of the total rainfall.
So this aspect, we consider that as best as we could. I mean, there is not so much information about the response of the perennial crops to water stress, but that was considered. The precipitation model works decently well in mesic to dry conditions. It is a little bit trickier if you are in a relatively wet environment and wherever the climate is dominated by frontal systems as opposed to convective storms. The reason being that in a frontal system you may have 2 days of rainfall one after the other, not because it happened, but because there is this frontal system passing. So in those conditions, I mean, probably here in northern Italy things would not be too good, because systems are relatively slow in moving around and stuff.
Serena, yeah.
Good question. So Did you consider rainfall parameters constant within a year?
Yeah.
Okay, so you did not really consider separate seasons related to growing phases of
No, but we are talking about like the main growing season for a normal crop would be like 60, 70 days.
Okay, yes.
So it's not,
Yeah,
it's
yeah,
not
yeah.
like,
Okay, so it's,
of course if you have an extreme seasonality
Yeah.
then
okay, yeah, yeah.
And also,